Welcome back to Geometry Classroom. Today we'll talk about geometric probability. But before starting our lesson, let's recall a few things about probability. In the previous lesson, we learned about probability, yes? And we defined the probability as a numerical value between 0 and 1 that measure the likelihood of an event. Yes? Remember, a probability could be expressed as a fraction, a decimal, or a percent. Yes? Now, in this lesson, we'll learn how to find the geometric probability and use the geometric probability to solve real-life problems. Now, geometric probability is used in a situation where points on a segment or in a region of a plane represent outcomes. It is found by calculating a ratio of two segments or two lengths or two areas, depending on the case. For example, first case is this one. In this example, we have to find the probability that a point, let's say K, is on a certain segment, let's say CD, right? Now, if we choose point K on a segment AB randomly, right? The probability that point K is on the segment CD, which is a part of segment AB, right, is the ratio of the length of segment CD to the length of segment AB, right? For example, a point is chosen randomly on segment PS, right? Find the probability of having that point on segment RS, right? RS. So the probability of getting that point on segment RS, let's say point K, yeah, would be the length of segment RS, which is 5, and the length of segment PS. So to find the length of PS, we simply use the the postulate of addition of segments, right? Segment addition. So we have to add them. 7 plus 13 equals 20, plus 5 is 25, right? So we can simplify this fraction, and at the end we get 1/5. Or if you like to express as a decimal, is 0.2 or 20%. That's the probability of having a point K chosen randomly on segment RS. Another situation is when a point K is chosen randomly on a region J, right? So, and we have to find the probability that point K chosen randomly in region J be in region M, right? Now, to find the probability, this probability, we need to find the ratio of the area of region M to the area of region J, right? Don't forget, the probability is always a number between 0 and 1. Good. let's have a few examples with geometric probability. This is, let's say, shaded region, right? Probably you don't see the difference, but that's why I mark it. In this example, it says a figure is created placing a rectangle inside a triangle. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded region, right? Good. Now, to find this probability, right? First, we have to find, right, the area of the square. The area of the square, remember, is the product of is the square of its side. Its side is 9. So area of the square would be 9 squared, which is 81, right? Good. Now, then we find the area of the triangle, right? The area of the triangle, right, as we can see, the area of the triangle is base times height over 2, right? Height of the triangle is 9, right? This is an isosceles triangle. The altitude or height cut the base of the triangle into 2 equal segments, which means this side would be 4.5 centimeters, right? And the whole base would be 9, right? The whole base is 9 centimeters. Now, how we find the area of the triangle? Using the formula for area of the triangle is base times height over 2, which is base is 9, height is also 9 over 2. So 9 times 9 is 81 over 2. So 81 divided by 2 would be 40.5. Yes? Now we have to find then, let's say, area of triangle. This is area of a square, area of triangle. And now the area of the rectangle, area of the rectangle would be length or times width, yeah? Length times width. Length is 4 and W is, or width is 3. So we multiply 4 by 3 and we get 12 centimeters. This is square centimeters, right? Remember, area is measured in square units. In this case, square centimeters. Now, what's next? To find the probability that the point chosen randomly in the whole region, which is the square, we have to find, we have to find the ratio of the area, the shaded region, over the total region, right? Now, to find the shaded region, we have to subtract the area of the whole triangle and the area of the rectangle, right? So, on top, you're supposed to have 40.5 minus 12 over the total area that we have, which is the area of the square. And the area of the square is 81. Right? So, on top, you're going to have, if you subtract these numbers, you're going to have 28.5 over 81. Yes? Now, how we simplify? We multiply by 10 both the numerator and denominator, and you're going to have 285 over 810. Probably, if we, let's say, let's use a calculator to find this ratio. Remember, the probability is a number that is less than 1, but larger than 0, right? So, let's find control divide 285 divided by 810, right? Hold on. 810. Control and enter. So you have 0.351. Or, if you like, about 35.1%. That's the probability of having a point chosen randomly in the whole area of the square that would be in the shaded region. Yes? Now, another example. The figure shows a circle with center O, right, and radius 8. Angle BOD is 72 degrees. The radius of the smaller circle is 4 centimeters. A point is selected at random inside the larger circle BCDE, yeah, the larger circle. Calculate the probability that the point lies A, inside the sector BODC. Remember, to find the probability, right, of having this point inside the sector BODC would be equal to the ratio of area of sector BODC over area of circle, right? Now, which is, as we know, the area of a sector, the area of this sector, right, is a part of the area of the whole circle, right? That's why the formula for area of a sector would be the ratio of the angle that is bounded by radii BO and OD, which is 72, right? Over 360 degrees, right? Times pi times the radius of the big circle, which is 8, but is square of the radius, right? So that's the area of sector BODC. Now, the area of the circle, we know, is pi times the square of the radius of the big circle, which is 8 squared, right? Now, as we can see, we can simplify pi and pi, 8 squared and a squared. So, at the end, you'll have 72 over 360. But this fraction can be simplified. So, you're going to have at the end 1 over 5. Yes? So, the probability of having a point chosen randomly in the circle B, CDE that is on or inside the sector BODC is 1 over 5 or 20%. Now, let's find the probability of having a point inside the smaller circle now. Yes? Now, the probability of having a point inside the smaller circle is the area of the smaller circle over the area of the bigger circle. Yes? Now, let's find the area of the smaller circle. Remember, is pi r squared, the formula. But the radius of the smaller circle is 4, yeah? So, you're going to have pi times 4 squared, right? And the area of the bigger circle would be pi times the square of the big radius, which is 8, yeah? So, we're going to have a squared. Again, we can simplify pi and pi, and what's left? 4 squared on top, 8 squared in the bottom. Now, if we do if we square 4, you get 16 on top. If we square 8, you get 64 in the bottom. But again, this fraction can be simplified. 16 is the largest factor, so you're going to have 1 over 4. So the probability of having a point inside the small circle is 1/4 or 25%. So that is all we have for today. Thank you for watching my video.